So without further ado, I'm excited to introduce our speaker for the day, who will be Dr. Brett Beaulieu-Jones. And Dr. Beaulieu-Jones received his PhD from the University of Pennsylvania under the supervision of Dr. Jason Moore and Dr. Casey Green, who's also joining us today. Beaulieu-Jones focused on using machine learning-based methods to more precisely define phenotypes from large-scale biomedical data repositories. After that, he joined Dr. Isaac Cohen's lab to do his postdoc, where he's been focusing on using ML methods to better understand the heterogeneity of neurological diseases, specifically Parkinson's and epilepsy. He is the former general chair and on the advisory board for ML for Health workshop, which is organized at NeurIPS. He is also the founding board member for the Association for Health Learning and Inference. And we're delighted to have him here at our journal club today, where he'll be talking about privacy-preserving generative deep neural networks for supporting clinical data sharing. So with that, I'll turn it over to you, Brett, and looking forward to the presentation.
Great, thank you very much. And Casey's here as well. And Casey, feel free to jump in at any point. And I'd invite any questions or comments as we go too, to make this as sort of interactive as we can. And I think the presentation should be about 30 minutes. So we have plenty of time for questions and discussion and to talk about sort of future directions and things like that. So I realized just a minute ago that I dropped my disclosure slide from this particular presentation. So I'll just quickly mention, I have funding from Sanofi, Merck, UCB, as well as I have started a company called Salutary that was acquired by Premier Inc. And sort of have equity in Premier and still have sort of consulting arrangements with Premier as well. And so that's sort of, I think, the key disclosure, some startup investments and things like that as well. And so our motivation for this work was really to ask the question, could we share data without sacrificing privacy? And this is probably the very sort of vanilla phrasing of this particular problem, where it had really started with the idea of sort of research parasites and led to sort of a much larger discussion from a New England Journal article about sort of secondary use of clinical trial data, especially, but other data types as well. I'll mention that Casey has started an award given every year at PSB called the Research Parasite Award. Some of you may be familiar with that, but it's now sort of two separate awards, where one is given to the group that shares data best, that leads to sort of the most effective uses, and the other is sort of for creative secondary use of data. And so it's really meant to encourage this ecosystem where both sides can come together and collaborate on. So I'd encourage you all to nominate people when nominations are. It may be late for this year, but Casey, is it past the deadline for this year?
I believe a recipient has been selected but not announced, okay. So keep your eyes out for next year.
Yep, so that sounds great. So with all of that sort of as background, we asked the question sort of from a technical perspective, are there things that we could do to create synthetic data that would allow us to sort of perform preliminary analyses? And I think it's really important to understand that our motivations are not to sort of replace analyses on real data, but instead to say, can we get realistic enough data that you can start doing your analyses when you have something promising? Then you can engage and do the sort of DUA process and all of the sort of administrative and legal overhead that's typically required to deal with data sharing. And so to sort of go back and sort of add sort of additional motivation around this, this is all the way back in 2010. Some of you may remember Netflix had a recommendation contest. In this contest, there was a set of researchers who actually showed that with very limited information, you could fairly accurately predict, particularly those who had multiple movies included in the data set, you could re-identify people. And so this is sort of the base premise here as a starting point, is that we need to acknowledge that de-identification does not mean that you're anonymous, and it does not mean that you cannot be re-identified. And so it's really important to clarify usage of those terms. And depending on who you talk to, de-identification could mean many different things. And even in HIPAA has sort of multiple definitions. And so as a sort of a further example of this, all the way back in the 90s, there's a researcher at MIT at the time, she's now at Harvard in the Kennedy School, Latanya Sweeney, who took data that the Massachusetts Group Insurance Commission had released and was able to actually, with a very limited set of data, re-identify the governor. And it's sort of a funny story because she actually mailed the governor his records in the mail to sort of demonstrate that it was possible to re-identify people. And so this is, again, to sort of provide additional motivation for why it's really important to get privacy right and to understand what we mean as we're talking about different levels of de-identification. And so we started by sort of using, it was actually really cool that we were able to use a data set that was in some ways the motivation for things like the Research Parasite Award, and had really started a lot of the discussion when New England Journal sponsored the Sprint Data Analysis Challenge, and actually released the clinical trial data for the Sprint trial. And so within this, if you just look at sort of the way to get access, and we actually had to go through this, it does require, despite the fact that the data are de-identified, you need to go through an IRB and have a DUA signed by your institution. And that usually means by going up to sort of the couple of authorized signers who have sort of the chosen pen that is allowed to sign off on these types of things, and can actually take quite a while and be a difficult process. And so we started out by asking the question, could we take these trial data, simulate them in a way that is realistic enough that they're useful, and then potentially distribute them to other researchers to perform analyses. And so to do this, we use what's called the Generative Adversarial Network. I won't spend too much time technically describing this. I think there's, as you mentioned, a fair amount of trainees here, and these are now not such new methods, sort of first popping up in 2014. But the basic premise is that we have a generative model and a discriminative model. And what we're trying to do is to, from a set of values chosen from a coordinate space, generate realistic enough samples that we're able to confuse or prevent the discriminator from learning to differentiate between the synthetic and the real data. As we train these two things together, it's essentially a mini-max game. And again, I won't get too far into the technical details here, but they're training in parallel, where the generator is trying to outsmart the discriminator, and the discriminator is constantly improving in its ability to discriminate. And this leads to better and better sample generation over time. So if we think about it from the perspective of what's actually happening here, going all the way back to the original GAN paper, we can have this sort of dotted line that is the discriminator trying to discriminate between two different distributions, one being the real distribution, this white dotted line, as well as the synthetic data distribution. And over time, what we learn is that the synthetic distribution can mimic the real distribution and be very hard to discriminate between the two data sets. And so these have gotten quite good. These are all actually not real images. They're generated by GANs. This is just to show sort of the progress that took place in between 2014 and 2018. Our work was initially published as a preprint in 2017. And so it's sort of in this time range of when this paper was being developed. And you can see sort of the quality of image that was already able to be created. And so to make this useful in the sort of clinical trial setting, knowing that we have two groups in a trial where for Sprint, it was intensive blood pressure management, where additional medications were given, and sort of traditional blood pressure management following sort of the guidelines at the time. And so within these two groups, we could consider them classes when we have to generate data. And so we need to learn to generate these two different groups. And that's where what's called an auxiliary classifier generative adversarial network comes in, where now we also are passing in a class label to the generative model. And so this is requiring the generator to not only create realistic samples, but create realistic samples of each class. And the way that is actually measured is by having the discriminator also predict the class. And so what we hope is that the class prediction goes up and the real versus simulated prediction goes down. And that's the way that these are sort of trained in parallel. These are, again, sort of looking back, and part of the reason I show this particular example is This was the original AC-GAN paper. This is sort of the core sort of starting point for our work. And I think it's important to note that these images don't look nearly as good as some of the others that I'll show sort of since this time period, and sort of would encourage people to sort of take the older base methods, and we've seen this in the literature quite a bit, where they've taken even our paper and built upon it to sort of improve the way that the data are actually generated. But this gives sort of what was state of the art as we were working on things and developing our project. This is just an example showing that since then, people have been able to do some really cool things, where particularly in imaging data, and I know there's a radiology focus here. We were not working with imaging data, but most GAN projects are. You can see sort of the ability now to manipulate images in sort of strategic and meaningful ways. And so whether it's adding eyeglasses to somebody or changing the way that somebody's face is actually pointed, these methods have gotten better and better.
Not an important one.
And so there are other works demonstrating these applications in different areas, whether it's sort of adding background or sort of turning an image, doing all sorts of other manipulation. This field has been quite active. Finally, I mean, just to give another sort of, I think, important example is when we look at sort of the progress in the field. This is a more recent paper where this is more in line with the type of task that we're actually thinking of here, where we're generating from some sort of base example, but we know it can't be perfectly matching. And so this is, I think, really interesting because they're generating all the way from sort of sketches and able to generate images. And I show these mostly to say the field has come quite far. And so when I present some of our work, I'll talk about some of the things that people have done since then that I think could improve upon what we did and build upon it. And so with this is sort of an example of the type of data we're actually generating in the trial. So the sprint trial was looking at blood pressure over time and looking at patterns. And so one of the things that we do is to actually generate these trajectories for synthetic patients over time. And so the first thing is to say that we were sort of able to train sort of vanilla GANs at the time to generate these patients and to start to separate them. And I think sorry. So this is the actual real data, and then this is sort of the generated data, or example of the generated data, and showing different sort of how close you can get with sort of a vanilla GAN. I think the key here is that is all sort of saying, okay, we can take a GAN out of the box, apply it to some clinical trial data, generate some data that look like sort of the actual clinical trial data, but it's not actually adding any privacy. There's no guarantee that the GAN is not, at this stage, not just memorizing the real patients and sort of spitting it out. And there's no actual privacy added, particularly if you are training this on some of the small clinical data sets. You could actually pull out a lot of information about patients from particularly the parameters in the model. And I won't really spend much time on this other than to say, as you look at sort of these training set sizes, there was a paper that came out back in 2016 showing the ability to perform what are called membership inference attacks. So to tell if somebody is actually present in the data set or not, particularly on sort of the training set sizes that we would expect to work in, even sort of off the edge over here to the left. It's quite possible given the parameters and sort of a non-private neural network. This was shown, again, sort of repeatedly on different data sets where you don't even need the parameters. And so these are using APIs for large shopping data sets and the ability to, from the recommendation engines, actually determine whether somebody was present in the data set or not. And so this was all motivation to us to figure out how we could generate synthetic data that had some guarantee of privacy. And so that really came to be when Casey and I were fortunate enough to be at Penn at the time, where Aaron Roth, who's really one of, I think, the core sort of leaders in the differential privacy field, sits and worked very closely with one of his graduate students, who's now at Carnegie Mellon, Stephen Wu. And so Stephen was a differential privacy expert. And so we worked closely on asking the question of how we could integrate differential privacy into our GAN. And so to give some background on differential privacy, one of the, I think, most important components of it is that it offers a mathematical guarantee. And that's really the core thing here. There's all sorts of things that have been done in the past that involve adding noise or sort of different approaches that theoretically add privacy, but it can't be quantified. And it's something that, particularly if you were to take to a lawyer or a policymaker, it doesn't necessarily mean anything to them because there's no way to understand what the adversarial attacks to it could be. But as we add privacy, one thing that is sort of a core tenet of differential privacy is that the more privacy that we add, the less useful, sort of by principle, the data become. And this is sort of, I think, fairly intuitive as you add sort of noise and limit the signal in the data and how identifiable any particular instance is, it becomes a little bit less useful. And so the trick is really finding the balance between those two things. And so to give, again, sort of further intuition behind what differential privacy is actually doing, it is sort of this example where if we had everybody in the room and we asked them a question and everybody flipped a coin, the people who had tails come up, answered the question truthfully, the people who had heads come up, give a random answer, and then we sort of compiled those. Doing that enough times, we come up with sort of the real solution to the problem. But there's obviously quite a bit of noise. In practice, we wouldn't have it be 50-50. The likelihood that you're giving a false answer would be far smaller, but directly correlates with the actual privacy level. And so the reason that this actually generates privacy is because there's a sort of deniability of any possible outcome. We don't know if somebody gave a truthful answer or not. And therefore, it becomes really hard to do any type of membership inference attack. Within machine learning, the ways that we can sort of apply this to deep learning particularly is by adding noise. And it used to be sort of purely Gaussian. Now there's a number of different strategies to this during the gradient descent process. And so every time that you're sort of taking a step, you're adding a little bit of noise and essentially preventing the parameters from either overfitting or learning too much information about or taking too much information from any single sample and preventing the network from including identifiable information about those samples. Within differential privacy, we have to constantly sort of consider two main parameters. And these are epsilon and delta. And this is the reason that frequently you'll see it called epsilon delta differential privacy. And in this case, epsilon is sort of the margin for which will allow information to be included, and delta is the chance, essentially, that the likelihood that the result is something outside of epsilon. So essentially, the chances that the differential privacy fails. And so now all of a sudden we have a sort of quantifiable privacy level that can be added. And so again, sort of intuitively, as we add more noise, we have greater privacy, but the network finds it a little bit harder to learn. And so when we think about this in the context of a auxiliary classifier GAN, we really think about it here, because the only place that we're ever incorporating real data is around the discriminator. And so this is really what needs to be private, because this feeds the rest of the network, and we don't need to be concerned about the generative model that is pulling from a coordinate space, because it is really learning from the discriminator. And so with this, I think an important principle to mention around differential privacy is that it is robust to post-processing. So once you have passed something through sort of a differential privacy layer, you can do anything you want after the fact. As long as you're not passing more information through that differential privacy layer, the mathematical guarantee holds up. And so this is sort of the principle here, where as long as this discriminator is differentially private, the results and output from any generative model that is learning from the discriminator and never actually seeing the real data are also differentially private. And so again, to sort of make it very simple in practice, the ways that we do this are we clip sort of the gradient, so how big any single step can be, and put a limit. And the reason we do this is to make sure that we're adding a proportionate amount of noise to that particular gradient. If any one gradient was too big and we were adding sort of a static amount of noise, potentially we would sort of lose the differential private guarantee. And so this allows us to make sure that for each given step, an appropriate level of noise is added. And as we train over time, we sort of accumulate sort of privacy loss, but we can sort of specify a level of epsilon and delta that we think is appropriate and for the particular application and use case. So initially when you do this, and this is where I was talking about adding privacy to a neural network, if the noise is too high, it can become very hard to learn. And so this is just showing, in this case, the two reds are the actual real trial data showing the mean values. The blue values are sort of the GAN that we had shown before when we just train it just off the sort of base data, at least sort of one application of that. And then, and then the purple values are sort of if we just immediately start adding noise without actually doing any correction. And as you can see here, that this systolic blood pressure is jumping up to quite a high level. And that's sort of the mean value and showing that it's generating lots of unrealistic values. And so eventually we, in one of the things that we did in the paper was to overcome this by not choosing any sort of single epic stopping point, but instead being a little bit smarter in choosing an ensemble of stopping points to generate these samples, which allows us to sort of balance the chances that we stopped at a step where the noise sort of outweighed the signal in the last couple training steps, because that can happen, and particularly as you go further and further into training a model. So this was after 500 epics. What happens in practice is that we don't necessarily want to train to sort of a full stopping point, but instead choose an appropriate point to stop. So that was one of the, I think, critical things to get right in this work. And so when we have these data, it's one thing to say, okay, we can generate data that have a mean value that are sort of on par in a trajectory that looks somewhat like the real data, but it doesn't really tell us that these would ever be useful for anything. And so we asked the question, could we start to test the sort of usability of data generated through a differentially private GAN and actually do a similar task where in one case we have the real training data going through some machine learning task, as well as the real data going into a differentially private, a non-private GAN. So this is the sort of the comparison of if we just create synthetic data, and then we eventually also go to a differentially private GAN. So this allows us to train sort of three separate models and ask the question of how does the, different source of data, whether it's the real data, the sort of traditional GAN or a private GAN, lead to different outcomes and sort of how do they affect the training of a machine learning classifier. And so when we do this for tasks, the nice thing is that we can see we're not losing a ton of signal. It would be sort of surprising if we didn't lose some signal, knowing that's the process that we're going through. But this was sort of a nice sanity check to say we're coming pretty close to the real benchmark, and there may be some utility in the data. And so this was, I think, a nice starting point to this. We also performed a different sort of statistical correlation test to ask whether we maintained the sort of same correlation structure of the data and did a lot of sort of the descriptive statistics sides of things as well to sort of compare to this as well. And then this was great, and we don't know necessarily maybe using something like, and the reason we use different classifiers is to say, we don't want to just use a neural network that happens to learn some alternate way of getting to the same answer, where maybe the data that we're passing into it are not real, but somehow we're giving enough that it can still capture the signature. By using different models, we can sort of see that effect, and we'd expect that maybe a random forest out of these the most could learn some artifact in the data that would be helpful there. But another way was to actually present the trajectories to clinicians and ask them to try to differentiate these. And so this is nice because it sort of parallels the thing that we commonly see in imaging GAN papers, where you'll see a real face versus a fake face and try to guess which one's real or fake. Here, there are, I think, some nice parallels, but there's also sort of things that clinicians would just know are unrealistic about data. And so there's some sort of clear, obvious giveaways if you're not doing well enough generating the data. In this case, we gave them sample trajectories and asked them to score them from 0 to 10 based off of how realistic they thought the data were. So basically 0 if they think it's fake, 10 if they think it's real. As humans are sort of want to do, they very rarely were especially confident in their predictions. But you'll see the blue is actually the private GAN data, and the green is the real data. And so we actually see in some cases they're thinking that the differentially private GAN data are more real even than the actual real data. This is reassuring in some ways. I'd almost say that it's potentially concerning because we know there are problems of mode collapse in GANs and other things. And so if we're just learning to generate sort of very typical patients, it's something that we have to think about and improve upon in the future. And so with that, I actually pulled this slide directly from 2017. I started editing it and decided that it would be better to sort of leave it as was at the time and sort of say what the state of the art of the field was and some of the key problems that existed, and then give a couple of examples of people who have improved upon both our methods and other methods sort of generally in GANs. And so at the time, especially, I think this is still true, but GANs are difficult to train. You can run into issues like mode collapse, and it's something that is still not completely solved. There's lots of techniques to sort of avoid it. In some ways, GANs, at least sort of at the time, especially felt almost more of an art than sort of a pure science. And that's why I think in the years 2017 to 2020, you probably saw every possible acronym before GAN and after sort of describing some slightly different flavor. Different ones have sort of won out over time and demonstrated that they're more effective. Another challenge, particularly at the time, that is somewhat solved now, and I think there's still a number of promising methods too that could be applied to clinical data, but haven't yet, is that neural networks have traditionally not been particularly good at mixed data type. And so this is the idea that as we have clinical data that typically are mixed between binary, categorical, and sort of continuous values, it's not easy to use one neural network to sort of generate each of those, given you have to have things like activation functions. And typically the sort of traditional way was to have a sigmoid function at the end for a classifier when you're predicting something. And so that would be great for a binary variable, but wouldn't work so well for a continuous value. And finally, one that I don't think has particularly been solved and is still relevant, despite a lot of attempts to train deep learning methods on smaller data. You do require quite a few samples, and in many cases, more samples than typical clinical trials. The SPRINT clinical trial, and I think generally you'll see this around hypertension trials and certain other sort of very common disease trials, had a much larger sample size than many sort of subtypes of cancer and things like that, where you'll be lucky to sort of see 100 patients in each group in each arm of the trial. And so that being said, I think just to sort of drive home the point is that there's a huge number of papers that have tried to do a lot of work on improving methods of GANs. And if you just look at the citation counts of some of these that were coming out around the time that our original work was done, and we couldn't necessarily even incorporate because we were sort of already into the publication pipeline, you'll see sort of quite a wide usage and sort of the popularity of these types of techniques. Additionally, there are at least, I think, 3 interesting papers that are directly relevant in terms of clinical data, where Stephanie Hyland had been working on using essentially recurrent neural networks to generate time series around the same time as us. We, in parallel, sort of got asked by reviewers to take parts of each other's papers that had been preprinted to improve our methods, where we demonstrated a second application in Mimic that actually used a recurrent approach. And she was asked to incorporate sort of our privacy perspective. So reviewers sort of forced our papers to be pushed in a similar direction. And they were really sort of co-developed around similar times. And so otherwise, I think there's some interesting work even very recently in mixed data types, as well as doing things to ensure that you are learning sort of an appropriate correlation structure and able to sort of pre-specify that. Finally, I just want to sort of bring up a core challenge. This may be a paper that's familiar to this group, but it's from Zach Kohani's group at Harvard, where I'm doing my postdoc, where Sam Finlayson, who was a grad student, he's an MD PhD student who's back in the clinic now, demonstrated the ability to essentially create sort of typical adversarial attacks in ways where if we have medical AI systems making decisions, they could be fooled. And so the examples given here are largely around if you are requiring a diagnosis of something for reimbursement, or say in a radiology image, when you want to get a surgery or a particular procedure reimbursed, you also have to submit the image, because now the payer has some AI system that is determining whether they agree with your diagnosis or not. To many of the clinicians, that may sound like a sort of a scary future, and not something that they necessarily an area where they want payers playing. But given that potential, there's sort of an example of ways where you can start to sort of fool the system by adding adversarial noise. And so this is something that the reason I really bring it back and relate it to our work is that as you're generating these synthetic examples, you could theoretically build in the ability to generate adversarial examples and sort of use that to really, I think, improve your ability to generate these adversarial examples. And so it's sort of in some ways built upon what we've done, but also is, I think, a word of warning as we transition to allowing AI to potentially play a larger role in different decision-making processes. And so with that, I'd like to thank everybody who has helped and contributed to the work, sort of funding sources at the time. It's now been a couple of years since I was in the Green Lab, but many of these people offered really great feedback along the way, as well as my co-PhD advisor, Jason Moore, and especially Aaron Roth and his group, and Stephen Wu, who's a co-author on this, as well as my new lab and Zach Kohani's lab and all of the great people there as well. So with that, I'd love to answer any questions or be happy to have a discussion. Thanks.